NOP. It sounds like the name of an ancient nihilistic god, but it's actually the name of an assembly instruction that does nothing. You'll sometimes hear people say NOP, and it turns out x86 has not one, but zillions of forms of NOP. What's the point of having zillions of instructions that do nothing? Which of these zillions of instructions is the best one for us to use? If you look at the x86 opcode table, you might even wonder if the NOP instruction was an accident. The encodings for basic 1-byte instructions like push and pop were decided on way back in the 1970s. As you can see, the low 4 bits are used to encode the operand register. For example, the opcodes operating on CX always end in a 1. That bottom row is instructions for exchanging AX with another register, and the first entry, hex 90, exchanges AX with itself, which doesn't accomplish much other than to advance the instruction pointer by 1 byte. So maybe the Intel engineers were like, that was totally on purpose. In fact, we're going to give that instruction its own mnemonic, NOP. Actually, it was almost definitely by design. The NOP has uses. If you're hacking an assembly code, you might use NOP to patch out other instructions for debugging. You could also use it for padding if you wanted to fall through to some code that had to start at a specific address. Many compilers will put NOPs between aligned functions, although I suppose theoretically they could put any junk they want there. Note that we had to use 5 NOPs to patch that function call. That's a lot of instructions. Is there a better way? What if we replaced it with a jump instead? The Intel optimization manual actually has a discussion of how to best fill multi-byte gaps with NOPs. Starting with the Pentium 6, there's a special 2-byte NOP instruction, and a 3-byte NOP, and a 4-byte NOP, all the way up to 9 bytes. There's also a special floating point NOP. The engineers at Intel have clearly spent a lot of time thinking about ways for their CPUs to do literally nothing. Maybe they should have spent that time working on other things. Let's see what AMD's optimization guide says. Wow, AMD looked at Intel's 9-byte NOPs and was like, those are rookie numbers. We go up to 15-byte NOPs. And their stock is doing quite a bit better than Intel's. On second thought, maybe Intel needs to spend more time on the NOPs after all. It turns out AMD's recommended multi-byte NOPs are, of course, perfectly compatible with Intel CPUs. If you saw my phmin POSUW video, we encountered a variant of the 15-byte NOP, although it didn't actually execute because in this case it's just padding between functions. And that's right, I said variant. There's more than one way to make a 15-byte NOP. A lot more than just one way. Let's look at the one on the screen. What the heck is even going on with all those bytes? And why is the RAX register involved in an instruction that doesn't do anything? Let's decode it. Those 66s at the beginning are operand size prefixes. They change the operation from 32 bits to 16 bits. It's allowed to have several copies of this prefix. The 2e is another prefix specifying that we will be addressing memory in the code segment, which has no effect because this instruction won't actually be dereferencing any memory. I don't know why the compiler put a code segment prefix here instead of another operand size prefix, which is what AMD recommended. Perhaps it was faster on their benchmarks on some specific CPU. Now we get to the actual opcode, 0f1f, which specifies the multi-byte form of NOP. Here we've gotten to the complicated part, which is decoding the instruction's operands. This next byte is called the ModR byte, hex 84 here. Looking it up in the appropriate table, we see that there's going to be a 32-bit displacement coming up, and that's going to be preceded by a scale index base byte, or SIB. Here its value is 0. Looking up 0 in the appropriate table, we see that the base register is EAX and the index register is also EAX. This is the 32-bit table, and since this is 64-bit code, both are actually RAX. The last 4 bytes are a 32-bit displacement. Again, this value won't be used by the CPU to actually dereference memory, so it can be any 32-bit number. Here, the value is 0. That was a lot of work just to decode 15 bytes, and the CPU has to do all that work too. According to the optimization guide, the CPU not only decodes all of that, but then it treats racks as an actual input. This means it's going to wait to execute the NOP until the value of racks has been fully calculated by any previous instructions. So for speed, it's best to specify a register that hasn't been used recently, whereas the 1-byte NOP is specially optimized without any register dependencies. So my question is it really faster to decode and execute all of that? How fast would it be to just have 15 of the old school NOPs? Or 3 5-byte NOPs? Or just have a jump instruction to skip ahead 15 bytes? I can think of a million ways to do this. I wonder just exactly how many possible NOPs there are. Okay, well, let's go down that rabbit hole. As we've seen, an x86 instruction consists of multiple components of varying sizes. The maximum total length of an instruction is 15 bytes. Let's start with those prefixes. From my reading of the docs, there are 29 possible prefixes. There's rules about how you're supposed to combine and order them. For example, it's undefined what will happen if you have conflicting segment override prefixes, and the rex prefix is supposed to occur in a specific position. I've found that none of these rules seem to matter on my CPU for the NOP instructions. I can use any of these prefixes in any order that I want and as many times as I want. The only exceptions, no pun intended, are the lock and VEX prefixes, which are illegal for NOP and cause a crash. So that leaves 26 possible prefixes. Moving on to the opcode, we've talked about 3 official NOPs. Note that there's other ways to do nothing. For example, you could use the LEA instruction to add 0 to a register. This is what some compilers would do for old chips before Intel introduced that 2-byte NOP. We could also use the add instruction to add 0 to a register, but that's not actually a NOP. The reason is that the CPU will update the flags register according to the result value. I'm sure there are plenty of other ways to do nothing. I'm going to stick to the 3 official instructions. The 1-byte NOP doesn't use any following bytes, but we can use up to 14 prefix bytes. In this example, I've thrown in a bunch of nonsense rex prefixes, and the disassembler is very confused. But the instruction actually runs just fine on my CPU. There are 64 quintillion ways that we could make a 15-byte NOP this way. It's a similar story for fNOP, but since it's a 2-byte opcode, we can use only 13 prefixes, so only 2.4 quintillion possibilities. Okay, let's talk about the 0f1f multi-byte NOP. The multi-byte NOP is always followed by a ModR byte, and sometimes also an SIB byte, and sometimes a displacement. Although the manual says 3 of the bits in the ModR should be 0, my CPU accepts all 256 possible values for this byte. If the SIB byte is present, then it too has 256 possible values. If there's a displacement, it can have 8 or 32 bits. Here are all the possible combinations of ModR, SIB, and displacements, if I got this right. And here are the number of possibilities for each type of encoding. Each of these can be prefixed to make a 15-byte instruction, so that's even more combinations. There's also the original NOP and fNOP, which we already talked about. Do the arithmetic, and this works out to quite a lot of NOPs. And I didn't even bother to add up the smaller NOPs. I've probably made mistakes in my math, and I'm probably reading the Intel manual wrong. Not that the manual even documents everything. The only way to be sure would be actually execute all of those NOPs, which would take forever. I'm reminded of an Arthur C. Clarke short story in which monks are attempting to use a computer to calculate and print all the names of God. Perhaps somewhere in the mountains, there are some monks with a cluster of servers trying to execute all the possible NOPs. I wonder how long it will take them to finish. Well, that's actually related to my first question, which is, which NOP is the fastest? Remember that there were 4 candidates: the 15-byte NOP that Clang omitted, 15 old-school 1-byte NOPs, 3 5-byte NOPs, and just use a jump instruction. I'm going to throw in a 15-byte LEA instruction as a late entry. For each candidate, I'm generating a giant function that's a big loop of 15,000 bytes of the appropriate NOP. My idea is to exceed the size of any front-end caches in the CPU. And here are my results. I can execute 6.2 billion of those 15-byte NOPs per second on my CPU. By the way, I also tested the AMD version with the 7 operand size prefixes, and it's just as fast. I can execute 17.6 billion 1-byte NOPs per second. It's now the leader. Are the 5-byte NOPs any faster? No, only 15 billion per second. The jump? Also slower, only 2 billion per second. What about LEA? By the way, did anyone notice that RIS register? It's a weird quirk of the disassembler. It's trying to show that even though I'm using the SIB byte, there's no scaled index register, so it puts a fake 0 register instead. As for LEAs per second, I only get 4.4 billion. So the winner is the original 1-byte NOP. I can execute over 17 billion of them per second. This number is pretty close to the theoretical maximum throughput for my Kaby Lake CPU. It can decode 4 instructions per cycle and turbo boost up to 4.5 GHz. So what was Intel thinking when they added that multi-byte NOP? The answer, of course, is that unless you're a monk trying to execute every NOP, it's not how many NOPs per second that matters. It's how quickly you can skip over the gap to reach the next instruction. We should be measuring bytes per second, not NOPs per second. By that measure, the real winner is in fact Clang's 15-byte NOP after all, 93 gigabytes per second, which is greater than the maximum throughput of my Kaby Lake's decoder. I guess I must not be completely defeating all of its caching. Here's how the other NOPs compare. The 1-byte NOP is actually the slowest NOP by this measure. But wait a second, let's take another look at LEA. I was only able to execute about 4.4 billion per second, but each of my LEA instructions is operating on the same register, RDI. The CPU can't add 0 to RDI until the value of that register has been calculated by any previous instructions. Is that slowing us down? Here's an idea. Interleave LEAs that operate on different registers. This gives us more time for the output of each addition to be ready to be used by a future instruction. This code executes just as fast as the original 15-byte NOP on my CPU, but the NOP is better because it doesn't seem to have the dependency chain issue. Another late entry. What about the original 1-byte NOP, but with 14 prefixes? This turns out to be just as fast on my CPU as well. So what's the point of the new NOP? The Intel docs say that prefixes can take extra cycles to decode, but apparently that's not a problem anymore. There's one other NOP I want to talk about. When the rep prefix is given to the 1-byte NOP, it becomes the pause instruction. This instruction is intended for use in spin loops and is designed to free up the CPU for another thread. Here, Intel optimized this instruction to save power, and it's really slow. I can execute only 312 million of these per second on my CPU. Well, that's it. You just watched a 13-minute video about CPUs doing literally nothing. I hope you got something out of it.